Welcome to this joint session of Section 7, Lie Theory and Generalization, and Section 9, Dynamics. I am Michael Pevsner, professor of Reims University in France. It is my pleasure to introduce Amir Mohammadi, professor of the University of California, San Diego. Professor Mohammadi got his PhD from Yale University in 2009 under the supervision of Grigory Margulis. He was a member of the Institute of Advanced Studies in Princeton and was awarded, among others, Sloan and Feynman fellowships. Professor Mohammadi made important contributions to dynamics and the Lie groups at the bordering area of homogeneous dynamics. For instance, he proved, with his collaborators, quantitative equidistribution of periodic orbits of semisimple groups in the S-Archimedean context, established strong density results of unipotent flows, and developed the positive characteristic Ratner theory. The title of his ICM talk is Finitary Analysis and Homogeneous Spaces. So please.
It is a great honor to be giving this talk. Like many others, I also wish that this was under different circumstances. Unfortunately, however, it is not. So today, I want to speak about dynamics and homogeneous spaces, and the emphasis will be on a quantitative aspect of the analysis. So some of the goal is to be able to write some rates for various rigidity results that we will be discussing. This is based on several joint works with many colleagues, and I hope to explicate this as we go along. So let me begin with a fundamental and celebrated theorem of Marino-Ratner about unipotent flows on homogeneous spaces. So I'm going to give myself a Lie group G and a discrete subgroup with finite covolume, so a lattice in G, and I want to study the action of unipotent subgroups in G mod L. What's the unipotent subgroup? Unipotent subgroup is so I'm writing the simplest case of this, a one parameter unipotent subgroup. I simply mean that I'm exponentiating some nilpotent matrix, and so exponential TZ where Z is a nilpotent matrix. So all the eigenvalues of this element UT are, all the complex eigenvalues are 1. Okay, and then I'm interested in understanding the behavior of UTX for every point X in G mod L. This is a highly non-trivial problem because different points may have different behaviors, and fundamental theorem of Ratner tells us that we can understand behavior of every point. So if I look at a test function and look at the time average along the orbit, this converges to integral of the function with respect to a nice measure. What do I mean by a nice measure, or rather, what does Ratner mean by a nice measure? This is a measure which is invariant measure on a closed intermediate orbit. So if I have, so one example of this L is then L equals G. So it could be that I am converging to the space average, but there might be some intermediate behavior. Maybe there is a subgroup which has a closed orbit starting from X and carries a probability L invariant measure, and the entire orbit is trapped in here. Of course, I need to account for this. But the gist of the result is that behavior of orbits, the orbits have nice behavior. So for example, as we will see in the next slide, orbit closures, if I just look at closure of this orbit, these are always submanifolds. Maybe they are proper, maybe they are they fill up the whole space, but there is no fractal behavior. It's always a submanifold, because I mean the LX is somehow the nicest submanifold you can imagine. This is a very strong rigidity result, and the point here is that it tells us behavior, it predicts behavior of every point. This is quite different from usual results in ergodic theory, where you have behavior of a typical point. So just somehow assuming some sort of ergodicity, which is essentially in all interesting examples is satisfied, you know that for almost every point, this behavior is the time average converges to space average. That is that's just a result about almost every point. But if you want to understand behavior of every point, this is somehow a much deeper, much more difficult problem where Ratner gives the answer. I also want to just mention that this is very different from the behavior of, if you look at a one-parameter diagonalizable subgroup, then one cannot expect any type of result of this kind because this action is going to be essentially, okay, in the case, let's say G was 2 by 2 matrices with determinant 1, then this the action of diagonalizable group is a Bernoulli action, and no such rigidity result can be expected. So it's a very deep result about unipotent dynamics. So Ratner's proof of this equidistribution result uses her measure classification theorem, and somehow, which the measure classification theorem itself also relies on polynomial-like behavior of unipotent orbits, but going from measure classification to equidistribution uses, again, polynomial-like behavior of unipotent flows, which were studied by Margulis and Danny Margulis prior to Ratner's work as well. And another remark, which I already mentioned, is that one of the motivations for Ratner's theorem was to prove Raghunathan's conjecture about topological rigidity, which is that suppose you are not interested in question about equidistribution, but just want to have some sort of a more qualitative analysis. So what's the orbit closure for every point? Of course, it follows from Ratner's theorem that orbit closures are nice. So closure of every orbit under a unipotent group, or more generally, groups generated by unipotent one-parameter subgroups, are submanifolds. So they are very nice submanifolds given by these periodic orbits. In this topological context, there were results prior to Ratner's work. Of course, Margulis proved the Oppenheim conjecture by proving a special case of Raghunathan's conjecture, or somehow some special theorem about a special case of Raghunathan's conjecture. And then later, Danny and Margulis strengthened these results, again, in the context of the Oppenheim conjecture. This topological approach was also used by Nimesh Shah, where he studies the behavior of one-parameter unipotent subgroups in quotients of SO and 1. So somehow in hyperbolic n space, the isometry group of hyperbolic n space. These items I'm mentioning are not in chronological order. So one of the first cases of this problem that was studied was the case of what's called so-called horospherical subgroups. What are horospherical subgroups? These are somehow big unipotent subgroups in your group. If you have 2 by 2 matrices, then you can just take a unipotent subgroup. But for bigger groups, like for n by n matrices, an example to have in mind is the full group of strictly upper triangular matrices. So these are stable or unstable, full unstable submanifold of some hyperbolic elements. So they're rather big. Algebraically, if you look at their normalizer is very big in the ambient group G, for example. So the quotient is compact. So if you take W to be the full group of strictly upper triangular matrices, the normalizer is the group of upper triangular matrices, and the quotient is the flag variety. So it's a compact thing. So these are rather big subgroups, and there are different tools to study them, and they were studied prior to the works I mentioned, beginning with the work of Hedlund, then Furstenberg, Beach, and Danny, and similar rigidity results is true for them. So in the simplest case, which is the case of 2 by 2 matrices, or rather in geometric language, I am looking at horocycles in H2. H2 is universal cover of a hyperbolic surface. And what Hedlund showed was that if you give me any horocycle and I look at its image in a hyperbolic surface, it either closes up or it's dense everywhere. And of course, the case that it's going to be closing up, this is only possible if your surface is not compact. For a compact surface, the horocycle will never close up, so every horocycle is going to be dense. This is minimality of horocycle flow. When the surface is not compact, you can have a closed horocycle which bounds the cusp, or if that's not the case, then it has to be dense everywhere. So this is in some sense the first examples of this type of rigidity result, of which Ratner's theorem is a vast generalization. Like I mentioned, I am going to be focusing on unipotent flows, but there were fundamental works in the context of the rigidity results for different group actions and also beyond homogeneous spaces. So I just want to briefly mention a few of these, and then we will return to the context of homogeneous dynamics. So if you are interested in group W, which is not unipotent, I already mentioned one dimension of the diagonalizable group, you don't expect any type of rigidity, is simply wrong, but a very interesting and challenging problem is what if this group W is a higher rank abelian, higher rank diagonal group or higher rank abelian action. And this is related to the Littlewood conjecture, and spectacular progress was made by Ketak, Einzitler, and Strauss. And where they proved that the set of exceptions to Littlewood conjecture has Hausdorff dimension 0. One can also be interested in group W that is somehow very far from being amenable. For example, maybe you are interested in action of a free group in a homogeneous space or action of Toral alomorphisms. This is the concerns of fundamental works of Bourgain, Foreman, Lindner, Strauss, Moses, and generalizations by Benoit Kahn, different techniques, where one studies random walks on G mod gamma. And the celebrated work of Eskin Mirzakhani on the SL2R action and the space of quadratic differentials. So somehow beyond homogeneous spaces and beyond unipotent dynamics on homogeneous spaces. Another interesting direction is one might want to relax the condition that gamma is a lattice. Maybe you don't want to assume finite volume. The fact that G mod gamma is finite volume is used in a very essential way in all these works. But the question of whether or not it's possible to obtain rigidity results in similar spirit for infinite volume spaces is also very interesting, and some work has been done in this direction as well. So I already mentioned several very strong rigidity results. There is one flaw to all the statements I mentioned, with the exception of one, and that is the work of Bourgain, Foreman, Lindner, Strauss, and Moses, which we will return to. And the issue is that all the works I mentioned, they somehow have this problem that they will never give you a rate at which you fill up your space. So suppose you start with a point and then you start flowing, and I want to stop at time capital T and ask the question, what parts of the space did I visit? Or what part of the closure I visited? And the results I mentioned will never tell you this. They actually, most of these works, they rely on phenomena that are very difficult to quantify or give a finitary analysis. For example, Ratner's work relies on Birkhoff-Ergodic theorem. The work of Danny Margulis relies on minimal sets, and these are very difficult to effectivize. And also, I want to mention that such an effective theorem will, in general, be complicated to state because it will depend on delicate behavior, delicate properties of the point and the acting group. Already for irrational rotation of circle, if you want to understand how dense the orbit becomes, this depends on how irrational your angle is. So here I give an example in the connected world or continuous world. So take the two torus, and I want to understand behavior of a line. So if I look at the line, which is almost horizontal, so it has a slope which is epsilon, so it's t epsilon t, and then I want to see how quickly this fills up the space, it very much depends on what chunk of the orbit I'm looking at. If I stop at time capital T, which is 1/2 epsilon, of this size, then I only see half of the torus. Even though eventually, so assuming that this epsilon is irrational, eventually this orbit will fill up the space. It really depends on how long I'm willing to wait. So it's always this kind of question of effective rates, or they will essentially always depend on delicate properties of the point and the orbit. So there has been some work in this direction also. And here I would like to give a brief history before mentioning the more recent developments. So I started with taking a Lie group and looking at the quotient of the Lie group acting by a subgroup. And as I have been somehow implicitly mentioning, I'm mostly interested in the case where G is a semi-simple group, so n by n matrices or the isometry group of some quadratic form. But the first case to look at in some sense is when G itself is a unipotent group. And this was studied by Green and Tao, where they give very elegant equidistribution theorem, and the rate of equidistribution is a polynomial. The proof there uses this fact that your group is unipotent in a very strong way. It relies on an inductive scheme and van der Kolk tricks. It's a proof that certainly cannot be generalized to semi-simple groups, but it gives a very beautiful answer for the case that G itself is unipotent. I also mentioned the case of horspherical subgroups. Horspherical subgroups are amenable to tools from representation theory and harmonic analysis. And these tools in general are by nature, they are quantitative, and they have been studied quantitatively by many people. I give some list of people here, and this by no means is a complete list. So we understand behavior of horspherical orbit and closely related to it, orbits of symmetric groups, meaning that they are fixed points of an involution of the ambient group because they're closely related to horspherical groups. And so, like I said, there's extensive work in here, and some of these works have decorations. The reason is that they are not, strictly speaking, horspherical work. So the work of Clausel and Olmo, this is on distribution of Hecke points. So somehow the reason it belongs to this list is, again, that an L2 estimate gives you pointwise equidistribution because of the fact that somehow two nearby points will have nearby Hecke orbits. That's why it belongs to this list. Strombergson has studied the case of semi-direct product. Let's a simple case of it is SL2R semi-direct product R2, so affine transformations, and the studies behavior of a unipotent which is horospheric in SL2. So in strictly speaking, this is not a horospherical subgroup of the big group, but it projects to a horospherical subgroup. And this has been generalized by Woo-Young Kim to the case of affine transformation in RSO, SL, and R semi-direct R, and the proofs are rather different, as I will mention in a minute. I mentioned the work of Burgan, Forman, Lindenstrauss, and Moses on random walks by toral alomorphisms, where they obtain polynomial rates for equidistribution. The tools used there are additive combinatorial tools, and I will return to this. I just want to here mentioned that Woo-Young-Kim's proof for the case of ASLN, SLN-R semi-direct product Rn, uses ideas and techniques from the work of BFLN. So it's very different from Strombergson's work, which relies on analytic methods. Some exponential sums. Another case that has been successfully studied in the context of congruence quotients is, rather than looking at arbitrary orbits, maybe one wants to just study periodic orbits of semi-simple subgroups. So you have a quotient, G is a semi-simple group, you look at the congruence quotient, G mod gamma, and then you look at periodic orbits of some semi-simple subgroup of this. This has also been studied, and a very deep result was proved by Einzidler, Margulis, and Venkatesh, where they prove equidistribution of these orbits with a polynomial rate. The rate is polynomial in the volume of the periodic orbit. This work imposed some restrictions on the acting group H. Some of these were removed in a follow-up work. And removing these conditions are essential for applications. For example, an application of this follow-up work was about the distribution of genus of a positive definite form in the space of quadratic forms. So some of these applications, when they're removed, they will have number theoretic applications, which are some of these restrictions. When they are removed, they will have number theoretic applications, which are quite interesting. The source of polynomial behavior here is uniform spectral gap for these periodic orbits. And this is somehow, again, is something that is restricted to the case of periodic orbits. One does not have this kind of uniform spectral gap tools to use. So the fact that gamma is congruence and a uniform spectral gap of these periodic orbits is essential for this work. If one is interested in general orbits, polynomial bounds are very rare, and until very recently, no such existed. But rates which are logarithmic or iteration of logarithms, these were proved or are in progress of being written in general case. So the first case that I want to mention is the work of Linder, Strauss, and Margulis in the context of Oppenheim conjecture. They prove an effective version of the Oppenheim conjecture. The rate, though, is logarithmic, depending on your point of view, is exponential. So if you want to find small solution for the Diophantine inequality QV less than epsilon, how big of a vector do I need? I need to take something that's exponential of 1 over epsilon to the n. Okay, and this is for quadratic forms which have Diophantine coefficients, and this capital N depends on the Diophantine properties of your form. Of course, in ideally, we would like to drop this epsilon exponential and would like to have a polynomial rate, but currently that's not available. And generalizing this type of argument, which is, one can arguably say that it's a descendant of Margulis's topological approach, or Danny Margulis's topological approach to proving Raghunathan's conjecture. One can prove a quantitative version of density result for general unipotent orbits, but the rate is very bad, very poor. It's an iteration of logarithms. So if you want to hit epsilon neighborhood of every point, the time you need is exponential of 1 over epsilon, where the number of exponents, it depends on dimension, or here I've written it in terms of the logarithmic bound. Now I want to maybe mention some recent developments where, as I mentioned, up until very recently, there was no approach to obtaining equidistribution or density results with polynomial rates for quotients of semi-simple groups, unless there was a very clear reason why one can prove it. You have a horospherical group, or you have a periodic orbit, and you have a uniform spectral gap to use. Thankfully, this situation has changed very recently, admittedly for very specific groups just now, but the approach seems quite strong and maybe possible to generalize. So I'm going to, from now till end of the talk, G is going to be one of these two groups, SL2C, or product of two SL2s. And then I'm going to take gamma to be an arithmetic lattice inside this. So an arithmetic lattice, I have already mentioned it many times, but explicitly you can think about SL2Z adjoint I. And in this case, you can think about either SL2Z times SL2Z, or the Galois embedding. Using Galois embedding, I can embed SL2 of Z adjoint I in here. So in here, you can think of SL2 Z adjoint I. In here, you can think of reducible or irreducible lattices, SL2Z times SL2Z, one example, or SL2Z adjoint square root of 2, where square root of 2 is embedded in R times R by using the Galois automorphism. So these are the examples to have in mind. And then I'm looking at the space G mod gamma, and I want to study questions related to what we discussed in this quotient. So I'm going to give myself a subgroup H, which is a copy of SL2R inside this group. In the first case, okay, SL2R is a subgroup of SL2C. In the second case, there are, well, three ways you can think of SL2R sitting in there. It's either one of the factors or it sits irreducibly. And if SL2R is one of the factors, then the analysis of the action is easier because it's a normal subgroup, and in some sense, you can identify it as a parabolic subgroup, etc., etc. So that's not very interesting in a sense. So I'm going to look at this case that SL2R sits diagonally. Up to conjugation, this is the only irreducible way SL2R can sit there. And so this is the context. The context is the quotients of this, and the action is action of unipotent subgroups, essentially, of one parameter unipotent subgroups acting on G mod gamma. And because of the simple case I'm looking at, these one parameter subgroups are either inside SL2R here, or the interesting case that does not follow under whatever I discussed, you can think of it as the one parameter unipotent subgroup of the SL2R here. So this is the context, but first I'm going to start with a bigger group, and that's the group of upper triangular matrices in SL2R. And I'm going to discuss a topological rigidity result. So the topological rigidity result for the action of this upper triangular group reads as follows. As I mentioned, rigidity results of this type, they are rather delicate to state and depend on behavior of dependent properties of the point. There's a mouthful here, but before reading the statement, let's think about how the statement should look like. A quantitative statement should be that either I am effectively dense in the space with some rate, which we are trying to somehow make it polynomial, and that's what this theorem does, or there is an explicit algebraic obstruction, and that's item 2 here. So let's first look at the explicit algebraic obstruction. So there is a nearby point with a periodic orbit of this group H of low complexity, so that my point is very close to this point. And this somehow prevents me from equidistribution because I stay very close to this periodic orbit throughout my life, and there's no way for me to go everywhere in the space. If this doesn't happen, then I am dense in the space with some rate, which is polynomiality. So that's the type of theorem we're after. And there's this parameter delta, which is introduced here. This is at your disposal. So you choose delta. If you choose a small delta, then the obstruction is quite strong, but also density is weaker. You choose bigger delta, it's very easy to satisfy the obstruction, but then the density result is stronger when the obstruction fits. But if you somehow choose delta too big, then you will almost surely be in this case too, because there are many periodic orbits that can prevent you from becoming dense. But this is always the type of statement we're going to have is always going to be of this nature, that there is a give and take between what level of complexity you declare as low complexity, and that will dictate somehow what's the good rate of density that you can have. So again, the statement says, given a capital T, look at ball of radius T applied to your base point. This either becomes T to power minus something dense in the space. If not, the reason for it is that there is a periodic orbit of low complexity that was too close to the initial point, and that prevents you from becoming dense. So, like I mentioned, the point is the fact that we get density result with a polynomial rate in T. This is very different from what I mentioned here, where you have at best exponential, or in this more general case, you have an iteration of exponential or logarithmic, depending on your point of view. So this is the first polynomial rate for non-periodic orbits of groups which are not horospherical in quotients of semi-simple groups. Now, the proof somehow has flavors similar to works of Gambert, Jacobson, Sarnak, the Bourgain celebrated work of Bourgain and Gambert, and also the deep work I mentioned, Bourgain, Furman, Strauss, and Moses, and relies on tools from, our proof also relies on tools from additive combinatorics. Combinatorics really, more precisely, we use tools from incident geometry and the work of Wolf and Schlag on circular Kikea problem. We use the tool, some tools from homogeneous dynamics, namely Margulis functions, to study somehow coarse dimension transversally. And we use the spectral gap of the ambient space, very different from uniform spectral gap that appeared in the work of Einzidler, Margulis, Venkatesh. This is spectral gap of the space G mod gamma, not of the intermediate periodic orbits. So these are the main tools that we use. Hopefully I will have time to somehow maybe mention in more details the argument. As I mentioned, periodic orbits were studied by Einzidler, Margulis, Venkatesh, and they prove quantitative equidistribution result with a polynomial rate. The assumption there was that gamma is a congruence lattice. In my theorem, I also wrote here, in our theorem with linear shots, I also wrote that gamma is an arithmetic lattice. This arithmeticity is used only in the first phase of the proof, or opening of the proof, to establish some sort of initial randomness for the points that you have. If you start with a periodic orbit, you don't need this arithmeticity, and our tool will enable you to prove some quantitative density without assuming gamma is arithmetic, and you get density with a polynomial rate. So, like I said, and it's written here also, if gamma were arithmetic, this would follow from Einzidler, Margulis, Venkatesh. But it's, if you don't assume gamma is arithmetic, then that proof doesn't work because you don't have uniform spectral gap to work with. Our proof will give you quantitative density, and this has some application in geometry, which I want to maybe take a detour and explain quickly. So, and this is precisely why I emphasize that we don't need arithmeticity. There are examples of non-arithmetic hyperbolic manifold in every dimension constructed by Gromov and Piatetsky-Shapiro. The construction is very geometric. So you take two arithmetic hyperbolic manifolds, M1 and M2, but you assume that the arithmetic structures don't match. So the groups, they use different number fields, for example. They are not commensurate. So they are both arithmetic, but the arithmetic structures are different. But what you assume is that there exists a totally geodesic surface inside them, two of these, that these are isomorphic. So there are two surfaces, the same surface, that are sitting inside M1 and M2. Now what you do is you cut open M1, you cut open M2, and you attach half of M1 to M2. You get this new hyperbolic three-manifold, which is no longer going to be arithmetic. This is not going to be arithmetic because the top and bottom, they have different arithmetic structure. And both of these are going to be Zariski dense in your group. If it were arithmetic, then the arithmetic data of purple and green would have had to be the same. So this is not going to be an arithmetic manifold. And here is more rigorously, more algebraically saying what it is. So I take M1 and M2 to three manifolds. I assume that I have two open submanifolds with boundary where the fundamental groups are Zariski dense and the boundaries are isomorphic, and I cut them open and I attach them to each other. So this gives a non-arithmetic hyperbolic manifold, hyperbolic three manifold, and then I can ask the following question: how many totally geodesic submanifolds does this new manifold have? There was a conjecture of Alan Reed and Kurt McMullen that this somehow this is a question of arithmeticity. If you have a hyperbolic three manifold which has infinitely many totally geodesic totally geodesic surfaces, then the hyperbolic manifold should be arithmetic. This was proved recently in the general case that I mentioned, independently by myself and Margulis, and also by Bader, Fisher, Miller, and Stover. But the case of these Piasecki-Shapiro manifolds, this was treated before. And a corollary of the theorem I mentioned gives a quantitative bound, polynomial actually, of the number of totally geodesic surfaces in these Piasecki-Shapiro manifolds. So what we can show is that the number of totally geodesic planes in one of these Piasecki-Shapiro manifolds is polynomially bounded in terms of the geometry of the manifold, the area of the surface you cut the two manifolds open, the volume of the resulting manifold, basically, some constants relating to Margulis constant or injectivity radius of the thick part, and then some mixing rate in X, so very, very explicit data. And the exponent is also related to the mixing rate in the manifold. So the upshot is that the number of totally geodesic manifold, totally geodesic surfaces in a Piasecki-Shapiro manifold, non-arithmetic one, is polynomial in terms of the geometry. So this finiteness theorem was proved prior to this more general case that I mentioned, and it was proved by Fisher, Lafont, Miller, and Stover, and also independently Benoit and O. And our proof uses the quantitative density about periodic orbits that I mentioned and some angular rigidity that was present in their work as well. So I just wanted to mention this application. This is a geometric application that is nice. So I have a few minutes left, so I want to now report on some strengthenings and generalization of the theorem I mentioned. This is joined with Linner-Strauss and along Linner-Strauss and Geraint Wang, where we were able to prove the first EQ distribution theorems with a rate, with any rate actually. So we prove it with polynomial rate, which apart from the power, this is the optimal rate you can hope for. But prior to this work, no EQ distribution theorem with any rate was known for general non-periodic orbits. So again, the context is the same. We have the group G, which is either SL2C or product of two SL2s. And then H is either SL2R or diagonally embedded SL2R inside this. And P in the previous theorem, in theorem A, I called it, was the group of upper triangular matrices in SL2R. Now I'm going to be working with two subgroups of this P, so the diagonal matrices and the group of unipotent matrices in SL2. So it's UR is this, and then AT is that, or is somehow more rigorously, it's the image of these in these groups. So diagonally embedded UR there or UR. All right. So this is the context, and the theorem is that we have an effective equidistribution theorem in these quotients. So again, gamma is arithmetic lattice, and I'm looking at G mod gamma. So it's the context is exactly the same, and then I start with a base point. And now I want to study, we will go to the case of long unipotent orbits momentarily, but first I want to mention this theorem, which is the push of time, some piece of unipotent. So I take the point x0, my base point, I apply interval 1 along the unipotent. And then I use the geodesic, this AT, the diagonal matrix, to expand this to make this longer. And then I ask what happens to this orbit. And the theorem says that either this piece of the orbit, which schematically this is, again, this is x0, I have u interval 0, 1 applied to x0, and then I apply a big piece of a log t, UR U01 X0. So somehow I change the base point in a sense when I'm applying this. So it's an orbit in a different point, but that's how it looks like. So I expand it, it becomes a long, complicated orbit, and then I ask what happens to it. The theorem says either this becomes equidistributed with respect to the G invariant measure on the space, or the reason it didn't become equidistributed is an explicit algebraic obstruction, very similar to what we had in theorem A. So if the distribution fails, then there is a periodic orbit with low complexity that's extremely close to your base point. That's what the theorem says. Again, the rate is polynomial, like I mentioned. Let alone the polynomial rate, no equidistribution result with any rate were known prior to this theorem. But we obtain the optimal one, well, optimal loosely speaking. The exponent we find is far from optimal, but it's optimal in the sense that it's a polynomial rate. And so a couple of remarks about this theorem. So like I mentioned, it's just now, it's not the long unipotent orbits. I will state the theorem about long unipotent orbits momentarily. This is about expanding pieces of the horosphere. So I apply time 1 of the unipotent, and then I push it down with AT to make it expanded. This theorem, of course, strengthens the density result I mentioned. The proof uses similar ingredients, but considerable refinement is needed. The proof is really much more involved than the proof of the density, and we need to work quite hard. And this theorem is actually theorem B, the way it's stated, is an effective version of the theorem of Nemes-Shah, where he proves this distribution of expanding pieces. Nemes-Shah's proof uses Ratner's measure classification and Danny Margoulis's linearization technique to go from long unipotent orbits to a theorem about pushes of unipotent. We go the opposite way. We prove theorem B, as I stated. We use linearization in its quantitative form, which was proved recently in a work with Lindenstrauss, Nemes-Shah, Margoulis, and myself. And then using these two, combining these two, we prove equidistribution theorem for long unipotent orbits. Again, what is the statement? The statement is you look at a long orbit, either you equidistribute in the space with a polynomial rate, or the reason the orbit is not equidistributed in the space is explicit algebraic obstruction. Algebraic obstructions in the case of long unipotents are more complicated. They can be more complicated than these pushes of unipotents. One could have analogous to what I wrote, an orbit of H, or rather a conjugate of H that's nearby, and the orbit is too close to this and cannot equidistribute. Or it could be that some periodic orbit of a unipotent group appears in one of the factors, or in G, or when G is product in one of the factors. And that's why it's not equidistributed. So it's captured by saying that the whole orbit can be pushed into infinity. So the theorem is more complicated just because the life is more complicated. It's not that we can't prove and we need to introduce these. It's just this is the reality. It could be that the unipotent orbit, this unipotent orbit is near a periodic orbit of a unipotent, and then it can be pushed into the cusp. It could be that it's near an orbit of H, or a conjugate of H, so it's not equidistributed. If these are not the case, then the orbit is equidistributed. I think my time is up. I was going to mention a few things about the proof, but okay, this is a good point to stop. Thank you.
Thanks to the speaker, Professor Mohammadi. Thanks to the audience. If you wish to interact with the speaker, you may join him on Discord, following the link available on the VICM website. Goodbye.